Hello and welcome to the Night Talk podcast. I'm your host, Lucius Knight. So the interview with the professor is finally here. Yeah, go ahead and celebrate. Or don't. There are some issues in this episode since it was a call-in. We did get disconnected a few times. There's lots of background noise throughout the interview. I personally feel like I seemed like an idiot throughout the interview, but I guess, you can make that decision on your, or distinction, whatever, on your own. There are some things we discussed that I'll have to actually listen to the interview again. But overarching theme, everything you know, there's no such thing as truth, and everything is just an assumption, is basically what I believe he came to. I don't know. But yeah, science is a useful tool, which, obviously, I'm not doing the interview any justice. You'll just have to listen to it whenever I finish this intro, and you can get past the intro music, and it actually jumps into the interview. Me talking isn't helping, but I'm gonna have to talk some more. So there's gonna be a follow-up episode where we provide commentary on the interview. It's gonna be funny. It's just I guess it could be like a 2-hour special. It's going to be long because we're going to listen to the interview and then just stop at different parts and then give our less educated opinions, or just talk shit. I don't know, just speak to make shit funny about the interview, because there are a bunch of parts in the interview, especially where the professor is speaking. I'm obviously lost. Oh, you can tell whenever you listen. I'm just I'm sitting there thinking, man, hope this guy doesn't think I'm an idiot. Hope he knew what he was getting into. But yeah, so yeah, I don't know when that follow-up episode will be recorded and uploaded. Hopefully soon. There's gonna be another episode. After this one, we're gonna jump into some more philosophy, or just stuff. That's not gonna be story time anymore. That's not gonna happen for a while. I might eventually, discuss my trip to San Francisco, but maybe not. We'll see. But yeah, we're gonna go back to discussing issues. I think we might discuss music, parties, and drugs in the next episode. So yeah, I look forward to that. I believe that's all the announcements that I have. But yeah, without further ado, this is the Night Talk podcast. I hope you enjoy. Hi, my name is Lucius Knight. This is the Night Talk podcast. I am here with the professor of philosophy of science from the University of Texas. Say hi.
Hi.
Hi. Yeah, so if you could just give me a little background about yourself and how you got into philosophy.
Yeah, thanks. Well, first, thanks for having me on.
No, it's my pleasure. Completely my pleasure.
I applaud your interest in having podcasts about issues like this. So, I've been interested in physics since I was pretty young, like elementary school. Mm-hmm. And I ended up in college when I went to Georgia Tech and thought I wanted to be an engineer, aerospace engineer, but I quickly figured out that I'm really more of a theoretician than sort of an applied person.
Yeah, I get that.
I'm not interested in building things or anything. I'm just interested in understanding things. Leave to others, how to build things.
Yeah.
So I majored in physics, and then I was going to get a PhD in physics, in theoretical physics. And I came to University of Texas at Austin to study with John Wheeler, who was Richard Feynman's advisor when he worked at Princeton. And I ended up meeting another physics graduate student who was really interested in philosophy. And I had developed a strong interest in philosophy during college as well. On the side, they didn't teach much philosophy at Georgia Tech. It's a very strong science and engineering, and there's less in the humanities.
Uh-huh.
But I read a bunch of philosophy on the side and was very interested in it, and I ended up spending most of my free time, as did my friend Robin Collins, who's now a philosopher at Messiah College. He and I ended up talking about philosophy all the time.
Yeah.
And we both decided to switch majors and go get our PhDs in philosophy.
Okay.
So he went to Notre Dame, and I went to the University of Pittsburgh, which has the best philosophy of science program in the country.
Oh, wow.
So anyway, that's roughly my history, and I'm still really interested in science, but I also just have very general interest in philosophy.
Yeah.
So that, yeah.
I do too. That's why we're having this interview.
Yeah, good.
Yeah, it's kind of funny. I myself went to school for mechanical engineering.
Okay.
Yeah, I got my bachelor's in that, but here I am talking about philosophy.
Yeah, it sucks some of us in, whether we want it or to or not.
Yeah. So, I've done, my knowledge of the philosophy of science is abysmal compared to yours. But if you could just, I guess, from your perspective, what is the philosophy of science?
So yeah, philosophy of science is really just trying to understand science as a phenomenon, how it fits into the big picture of understanding reality that philosophy is about.
Mm-hmm.
But then also particular important central issues or concepts within science. So, for example, the nature of scientific evidence.
Yeah.
What is it to be evidence for one bit of data to be evidence for another? What is for a theory, let's say, or a hypothesis? There are questions about how scientists have tested theories, but there are also questions that would be a descriptive question. There are also questions philosophers are interested about how they should be testing theories, whether they are doing so or not. So, for example, foundations of statistics and probability would be one of many philosophically investigated areas concerning, relative evidence in the philosophy of science. Another issue would be the nature of causation. So causation is notoriously, let's say, obscure or controversial in the history of thought.
Mm-hmm.
And there's some philosophers and some scientists, for that matter, who reject the notion of causation, but others who take it to be just absolutely essential to science and understanding the world. But then there are issues about, look, what do we mean? What could we possibly mean, and how could we possibly tell whether one thing causes another? What that comes to. And then related to that is an issue such as explanation. There was a couple of decades where philosophers tried to analyze the notion of scientific explanation. And to make a long story short, no one, well, in my view, and a lot of people's view, I would say, nobody really came up with a convincing general account of what explanation is, even though explanation seems absolutely fundamental and important to science and maybe even beyond science to philosophy. Like, what the heck are we doing when we intend to explain something? You might think that often connects to causation, like, well, here's what it is to explain, to show how one collection of facts or events cause some other events or facts. But that then connects it to this potentially obscure, controversial notion of causation. There are various approaches to explanation, but none of them have proven, like, very generally acceptable for a variety of counterexamples that come up. Another kind of issue in philosophy of science is the so-called demarcation problem. A philosopher named Karl Popper, Austrian philosopher, is famous for, in the 1920s, attempting to distinguish what's distinctive about science as an activity, scientific investigation, scientific theories from other kinds of activities that might seem to be scientific, but actually they're what he would call pseudoscientific.
Uh-huh.
And even today, we have questions about, look, is acupuncture scientifically supported, or is it a scientific account? Did the Chinese in 1000 BC, were they doing science when they were investigating acupuncture? Or was it some other kind of activity? Did science, as we perceive it, arise during the Renaissance, then the scientific revolution? Or has it been with us for thousands of years? This is connected to the demarcation problem, like, what is science? If there is a distinctive kind of activity that we should label science, what should it be? So that's another kind of issue connected with science,
So,
the philosophy of science.
kind of want to go back to causation and explanation.
Okay.
So, one would think that, explanation and causation would be kind of simple to explain. For instance, like, why does water boil? You would say, well, if you put a heat source underneath, pots of water, that causes the water to boil. And,
Yeah.
Like the heat gets transferred from, let's say, the stove to the metal pot to the water, and then that causes the chemical reactions which turns the water into steam.
Yeah.
And I guess if you were to run that quote unquote experiments over and over again and try to change the variables to see if it truly is the heat that causes the water to boil, then you come to a conclusion that it is heat. Wouldn't that be a form of explanation as to why water boils?
Well, it would be, in the sense that all of us would tend to accept that at sort of a common sense level.
Mm-hmm.
But if you ask, okay, this connects actually to another kind of fundamental question about the philosophy of science, the so-called theoretical entities, like, let's call them unobservable phenomena that aren't straightforward things like heat,
Mm-hmm.
that we posit to explain phenomena, because we say, well, there must be something transferred. Like, suppose before we knew about molecular motion, people knew about heat.
Yeah.
Or had some idea that there was, maybe some kind of fluid transferred between hot objects and colder objects, things like that.
Mm-hmm.
So that's a sort of a connected issue, but whether whether we're merely observing a correlation. Like, here, one of the fundamental problems about causation is, how do we tell whether we're simply observing a correlation. How do we get to this seemingly further assumption that there's a causal, that really the heat is causing the boiling, as opposed to, look, it turns out when water gets to a certain level of so-called temperature, little bubbles start forming in it. I don't know what this obscure notion of causation is, but here's the thing. We know that there are correlations of this sort, and we can sort of take advantage of these correlations that we learn about. So you don't need to bring in causation, just bring in various correlations.
So you're saying that we can, I guess, never know 100% for sure that the heat is causing the water to boil, but you can, I guess, infer from like every time that you get water to come to a certain temperature that it starts to boil. So you're just making that correlation between that temperature and the water boiling.
Yeah, you can, let's say it seems relatively or more straightforward to test for correlations.
Gotcha. Okay.
But then it seems like there's some further obscure bit we're adding when we say, no, there's actually a causal relation. Like, what does that really add, if anything? Is it just an obscure addition to basically, here's the thing, there's a correlation of a certain sort?
Gotcha.
We sort of tend to think there is an important difference between causation and correlation. Often we say things like, well, these two features are correlated. We don't know why. We don't know what's causing the correlation, but there probably is some cause or explanation for the correlation.
I got you.
But then question, what the heck do we mean by that, or what could we mean by that?
So, you can only strongly infer based on the evidence. Like, for instance, my freshman year in college, one of my professors, he made a distinction that in the summer, the number of crimes go up, but in the summer, also the number of ice cream sales go up. So you could say that the ice cream sales cause the growth in the number of crimes, but those could just be products of a different quote-unquote causation.
Yes.
Okay. Yeah, I see what you're saying.
So, I mean, there's a further distinction one can draw about, let's call them mere correlations of a certain sort and a certain kind of what's called a subjunctive.
Mm-hmm.
So there's statements of the form would, like let's say in the ice cream case, is it the case that if people were to consume more ice cream, they would commit more crimes on average?
And,
seems implausible, possible, but it is.
Would there be a way to test that? For instance, if you were really serious about trying to figure out what's the correlation between ice cream sales and, or maybe not necessarily ice cream sales, but just the consumption of ice cream with the number of crimes, isn't that where science comes into play? Where you have
commonsensically, again, we take ourselves to be able to establish subjunctive truths.
Uh-huh.
So, for example, if we set up experiments and we get a couple of thousand people, otherwise, let's say a couple of thousand twins, pairs of twins,
uh-huh.
and then one of the twin of each pair, we feed them more ice cream, the other pair we feed, less ice cream, or no ice cream or whatever, and then we check. Even that wouldn't be quite, you'd have to set up some test that you felt like was convincing.
Mm-hmm.
I'm worried now if we just pick twins, that's not a random sample of the population.
Understand.
Could be ice cream causes twins to commit more crimes. Anyway, we would take certain kinds of experimental results to at least support subjunctive truths.
Mm-hmm.
But there's something weird about subjunctives also. Maybe not quite as obscure as causation. Maybe it's a similar kind of obscurity, but we can never check what would have happened if we hadn't done something.
Yeah.
So in some sense, all we can ever find out about by observing is what happens in the actual world. If somebody says, well, this didn't happen, but if we had fed these other people more ice cream, they would have committed more crimes. somebody says, well, so you say, but how can we check that? That's always a claim about something that we can't possibly observe. It's something that could have but didn't happen.
Yeah. So you.
So
would
it's
have
as
to,
though
like, go back
we're
in
trying
time.
to make claims about other possible worlds that aren't the actual world.
True. You would have
So
to.
that's part of the difficulty of explaining why, let's say, some facts that we actually observe in the actual world are supposed to bear on what could have happened in some other non-actual world.
Yeah. So you'd basically have to be able to observe different forms of reality where different things happened at the same time.
Yes, which we can't, right? It seems like anything we actually observe is an aspect of the actual world, you might think.
Yeah.
I'm not saying that's obviously correct, but it seems to me a pretty, most people would accept that.
I want to go back a little bit. You said subjunctive truths.
Yeah.
I don't know if most people would understand what that is. Could you elaborate just a little bit?
Yeah, they're very common. It's Wood statements, basically. Like if I had stayed up all night drinking, I would feel really bad right now. I would have a headache.
Uh-huh.
We say that stuff all the time. But there's this issue about, look, how could we possibly settle Wood questions definitively if somebody raised doubts about them? Again, because all you can do is sort of find out what has happened in the actual world. How does that bear on what would happen under some different circumstance that didn't actually happen?
Gotcha. So there's no way of knowing that, regardless of the amount of alcohol consumed, if you would have woken up with a headache or not.
Sorry, say that again?
That there's no way of knowing that regardless of the amount of alcohol consumed, whether or not you would have woken up with a headache.
Yeah, there's no way of knowing for sure, let's say.
Gotcha.
And this, one reaction to this worry is, well, that's sort of hyper-skeptical. Of course, we can establish Wood statements. But it turns out when you start getting into, for example, quantum theory
Uh-huh.
and certain experimental results raise problems with our common sense subjectives. Like if we had made this measurement, some other thing would have happened. Turns out to be very tricky to interpret when you come to the quantum realm. So in actual empirical results in physics raise questions about what we can assume about when we check for subjunctives, like what we can really infer from data, things like that. It's a somewhat long story in itself, but I'm just mentioning why, from a scientific point of view, and a philosophical point of view, it's an obscure question how evidence about an actual situation is supposed to bear on a merely possible situation.
Okay. So, like, from my very limited understanding of quantum science, what I seem to know is that an outcome changes if you observe it. That basically at the quantum level, like everything is basically just all of life is probability. And so, I guess in our reality, for instance, me picking up a pen, there's a strong correlation between me putting a force on that pen to go upwards to cause it to lift. But in another realm, that pen could have lifted without my touching it. Okay. So it seems like we're having some technical difficulties. I got disconnected from the professor. If you'll just bear with me, I'll try to get reestablish contact. Hello?
Hey, Lucius, sorry, I lost you when you were talking about the pen.
Yeah. What was I saying?
You were you were giving some sort of comparison between features of a pen and quantum.
Yeah,
cases.
so like for instance, God, I probably sound very incredibly wrong. Don't know what the correct word is, but like we would, let's say that if I was to lift up a pen, no exact force on it to force it to go up, you would never know if that pen was gonna go up without my interacting with it. Or for instance, all of reality as we know it, you really know it because of us observing it. I hope that doesn't sound confusing.
Well, unfortunately, you broke up a bunch in there again, but let me say a couple of things. It's true that quantum theory makes probabilistic predictions in general, but there is, in a way, that raises something I brought up earlier, which is interpretations of probability.
Mm-hmm.
It turns out that in quantum theory, one of the questions, in some sense, just is how to interpret the probabilities of quantum theory. So, for example, when one measures the position of an electron in a box,
Yeah.
There is this way of talking where that's what sometimes people say. It's as though the electron did not have a definite position until we measured it.
Mm-hmm.
That's, let's call it, metaphysical interpretation of a state change after measurement. So it's as though reality, the electron was, let's just say, like a cloud before measurement, and then it collapsed into a point-like, region when some interaction with a measuring apparatus came about. But there's another, in some ways, much more natural interpretation of what's happening, which is an epistemic interpretation. That is, what we know about the electron is what changes. So, for example, when we flip a coin and don't show it to you and say, what's the probability that it came up heads versus tails? You might say, oh, the probability is 50%.
Mm-hmm.
But what could you mean by that? Presumably, you don't mean in the coin case, the coin isn't definitely heads or tails until we look at it.
Yeah.
It seems like, no, the coin's definitely heads or tails before we look at it. So when we look at it, all we're doing is changing our information state. So one of the fundamental difficulties in interpreting what's going on in quantum theory is determining how to interpret the probabilities of quantum theory along, this kind of line. And the tendency has been, a lot of people think, well, it must be the epistemic probabilities there must be, deep so-called hidden variables that are somehow guiding the electron or something, and then when we measure it, we're finding out where it was just prior to measurement.
Professor? Hello?
Are you still there? Okay. I lost you there for a second.
Yeah.
That is one kind of issue. People use the word probability. This is one of my pet peeves. I'm sort of an outlier on this front, my personal views, but people use the word probability as though it's univocal in meaning, when in fact they're just very different things one can mean when one says the probability that so-and-so is such and such. And it makes a huge difference in interpreting various claims, including in quantum theory, but not just quantum theory, what we suppose ourselves to be meaning when we make a probability point. Now, let me say an interesting connection to that. There are so-called many-world interpretations of quantum phenomena you've probably heard of. So the idea is, let's say when we're measuring the position of an electron in a box, actually there's these infinitely many parallel universes, roughly, And each such universe, there's duplicates of us, right? More or less, getting measurement outcomes for the electron at the different possible locations it can be found to have.
Okay.
So their interpretations of what's going on as well, they're all these metaphysical different worlds out there, and each of us, our life history, our consciousness, for some reason, tends to be confined to one of these parallel branches. But it's one of many sort of strange, counterintuitive views that people have felt themselves pushed toward, some people, in trying to make sense of quantum phenomena. I mention this just as a way of partly of introducing the topic in case you want to talk about it more, but also to give you a sense that it's not as simple as just, well, here's the difference when we introduce quantum theory. It's just a probabilistic theory. That only barely scratches the surface of how bizarre quantum theory is.
Yes, I still don't understand quantum theory, and I probably never will.
Well, a lot of physicists, famous physicists, including Feynman, said nobody understands quantum theory.
Yeah.
So, that connects back to, here's another big question that I'm very interested in, is the question of so-called scientific realism.
Mm-hmm.
So question, does science is science geared towards, or should we think of science as revealing, let's call it the deep truth about reality, the real truth about reality? Or should we conceive science as a way of getting a better handle on correlations of various sorts that we can measure?
Couldn't one make the claim that those correlations are pretty much the closest we're going to get to, I guess, maybe not absolute facts, but just objective reality?
Well, so when we posit, I don't know, let's even say when we posit electrons, there's a kind of view that's sometimes labeled instrumentalism or a kind of pragmatism that says, here's what happens in science. You come up with theories that then predict pointer readings in the laboratory.
Mm-hmm.
So if we posit science and posit electrons, and we deploy a theory involving electron talk, and then we make a prediction and it says this pointer on this device is going to read 3.2, and then it does, and we say, okay, the theory's been confirmed, but don't think then there really are electrons. Instead, all we should think is, well, now we have a really good instrument for predicting pointer readings. It involves this word electron and other stuff. In other words, that's the sense in which an instrumentalist says, don't think of science as revealing the truth about reality. It's not that there really are electrons and all these so-called fundamental particles, 11 dimensions, or whatever the latest view is supposed to be. It's, here's this mathematical device for making predictions about pointer readings for instruments we can build. That's all it comes to.
Okay, so I guess...
And I don't mean that's all it comes to. It's supposed to be a minimal thing. That's an incredibly powerful and important thing.
Yeah.
But just don't confuse that with deep, some sort of metaphysical fact about reality involving electrons.
So, I guess that's kind of why there's always this margin of error whenever it comes to using instruments to measure what some would say, quote unquote, truths about the physical world. But with that in mind, couldn't you safely assume that, I don't know, I guess for instance, if you were trying to measure somebody's mass, well, you would first need to measure the gravitational pull of that person's mass from the Earth, which we have already done, and then you could use that knowledge along with their weight, which you would get from an instrument to measure that person's mass. I guess that in a sense is the closest truth we can get to that person's mass. Is that it's not 100% factual, but I'm guessing that's the closest we can get to the truth about that specific part of reality. Is that what I'm understanding?
Well, it's an obscure and difficult thing to think about, like what we could mean by the truth about reality. Mm-hmm. But an instrumentalist about mass would say, look, whether there really is mass, I don't know. That's an obscure metaphysical question, they might say. But here's the thing. We have measurement techniques together with instruments, that is theories and devices that make predictions about how various things are going to move and how much a spring under you is going to compress, depending on how much so-called mass you supposedly is attributed to you. Mm-hmm. So mass is a useful posit for making predictions, but don't confuse that with there's really mass out there in reality, whatever that would be.
Okay, so basically
Yeah.
all of science is just assumptions that with these assumptions, you can make claims about the physical world, but that doesn't necessarily make it true.
Yeah, and it's not even, that the evidence never supports, according to certain instrumentalists, the evidence never supports, let's call it genuinely supports claims about, the ultimate truth about reality. Yeah. Whereas a scientific realist tends to think, no, damn it, science reveals the genuine truth about reality. There really are electrons. Things really have a mass. Mm-hmm. And they take the fact that claims about mass make good predictions. They say that's actually evidence that it's really true. That's what a realist is liable to say. Whereas an instrumentalist says, well, so you say that that's evidence that's really true, but we don't see why it's evidence that it's really true as opposed to merely a useful posit. And, it's an argument that just to note, many philosophers take the realists to have won the argument, roughly. Uh-huh. But I'm not one of those. I think it remains very obscure what to think about all that. And quantum mechanics in particular makes it very difficult to sustain realism about quantum theory.
Yeah.
Because it's not even clear what the claim that would be true is of quantum theory, other than here's what's going to happen to some pointer reading trusses. There was actually a movement in physics in the the late 1950s, maybe mid-1950s, towards what's called S-matrix theory, according to which the goal of physics should just be to come up with a huge S-matrix, which is more or less a mathematical device for giving you all the probabilities of all possible interactions.
You said it's called an S-matrix?
S-matrix, the letter S is in Sam.
Uh-huh.
So S-matrix theory says, here's what we should be doing as physicists. Our goal is come up with the big S-matrix for reality, which is roughly, I would say, fits well with an instrumentalist view. It's, let's come up with a device that predicts all possible pointer readings in any possible experiment. That's all we should aspire to. That's all we could possibly accomplish, no matter what kind of experiment we do. But that didn't win out, for various reasons. And whether that would be good scientific methodology is an interesting philosophical question.
So I guess what people, well, me included, are really curious about is that, so people kind of want to know, I guess, they have this desire for an absolute truth. And
yes, that's true.
Feel like, well, science is some people say that science provides an absolute truth. Others will say science is the closest thing you can get to an absolute truth. While some people they don't consider science to provide any type of truth at all.
Yes, That's roughly right. And then, and there are various versions of each of those views, but yeah, that's generally the right idea.
So I guess from my understanding so far, through science, you have an assumption. You test that assumption to try to see what your experiment holds, and then you run that experiment multiple times to try to get to a truth. So I guess the next question is, how many experiments does one need to run before one can safely assume that this cause is correlated to this effect?
Well, that's a great question. This connects to there's a phenomenon you could call the theory-ladenness of observation, or you could sometimes label the Quine-Duhem problem of underdetermination. And it connects to what we take to be a test of a scientific theory. We don't test scientific theories in a vacuum. We always have to make assumptions, background assumptions about how the devices we're using work. Basically, we have this background theory of the world together with a bunch of assumptions, some of them common sense, some of them we're not even aware we're making until somebody, something weird happens, and then in the process of figuring it out, you say, hey, we're assuming that there's such a thing as simultaneity, and then Einstein says, you're wrong, there's no such thing as an absolute simultaneity. It's more complicated than that, right? So think of how many tests were run of Newtonian physics and various theories that were that were presupposing Newtonian physics. Basically hundreds, thousands, but they were presupposing a false theory. So there's a sense in which, and that's the situation everyone is in, including now. It's hard to imagine that the current physical theories are correct for various reasons. Basically, it's very hard to reconcile even the mathematical framework of general relativity, our theory of gravitation, with the quantum physics. The mathematical frameworks are so different. It's hard. Nobody has figured out sort of even remotely good or remotely testable way of pulling all of those parts of physics together into a single theory, so-called unified theory of everything. So we're always, and even if we did, we would be in the same boat as Newtonians were. Well, when we so-called test a new hypothesis, we're testing it against the background of a presupposed theory that may turn out, it probably will arguably turn out to be not quite right.
Mm-hmm.
So then there's a sense in which this talk of testing a theory and taking it to be a once and for all, you've just tested this hypothesis and the data vindicated it, that picture doesn't fit well with the actual situation in this sense that any test you do may be probably is presupposing a false fundamental theory that will be revised eventually. And
now when you say,
so what do we even mean by a test? It's not as though we sort of, okay, now we've settled this issue. It's, well, you settled it on the assumption that some background theory is the case.
So when you say theory, do you mean theory in the realm of science as the closest thing we have to that certain truth, like the Big Bang theory or the theory of evolution, or do you mean theory as how most people would associate theory with just a guess?
I mean theory in the sense that allows for it may be the best currently, or the best guess,
okay,
or the best current hypothesis. Yeah. By the way, when you talk about the closest thing we have to the truth, I would want to amend that to something more like our best current guess.
Okay.
Because what it comes to is, well, the Big Bang Theory, or some extension of it, some inflationary model, for example, now fits with a lot of the data. To say that it is in fact the closest thing to the truth, I don't know what to make of that. I feel like what I would prefer to say myself would be something like, it's currently the most plausible seeming given all the data that we've thought of so far, or something like that.
Okay, so basically take every single theory with a gigantic grain of salt.
Yeah.
All right, that makes
Yeah.
sense. Makes sense. I guess in that same boat, what we have as scientific laws, how do we come about that?
How do we come about
Yeah, so we have
coming up with laws?
Yeah, so like with theories, as you say, this is the best guess that we have currently based on the evidence that we have, and so for scientific laws, like the first law of motion, how do scientists make that claim, make that distinction between like that this is so fundamental that it has to be a law?
That's a great question too. So that's another fundamental question about science, is what the heck is a law?
Mm-hmm.
Are there any? And if so, what is a law? It's actually not unrelated to the obscurities pertaining to causation,
Mm-hmm.
because some approaches would say, well, somehow laws are closely tied to fundamental causal relations between kinds of phenomena or something like that. But anyway, short answer to the law thing is, I am unaware of any widely accepted view of what a scientific law is. It's very obscure what a law could be.
Mm-hmm.
Other than a relatively uncontroversial, let's say, it's a mathematical formula that's useful for making predictions. Everybody kind of agrees with that. But beyond that, like what would make something a law if it were? It also connects to this subjunctive stuff we were talking about.
Yeah.
Like a law seems to be a kind of thing we want to say would remain true even under different circumstances. You know, the law would have still held. And there are various views about laws. One is that the so-called laws are projections out of, it's sort of a best systematization of actual data that we observe. But other people think that no, laws are somehow truths about how any possible physical, for example, physical system could ever proceed or, you know, change state, something like that. So anyway, there's no good answer to what laws are. It's what short answer I would say.
Okay.
I don't want to say there's no good answer. There's no great answer. There's a bunch of plausible sounding answers, none of which seem to pan out when pressed, you know, when carefully analyzed on reflection.
I don't know if you would have the answer to this question, but do you think that certain laws that we have in our physical world would change when you get to the quantum world?
So I'm not sure what you have in mind.
Like, for instance, I mean, from my understanding, things are very, very different when you get to the quantum scale. So, like,
Yeah.
with two particles, like we have in our physical world, that if you put a force on an object, it exerts that same amount of force back on you. Would that be the same in the quantum world?
Yeah, well, that's a good example of how different quantum theory is.
Mm-hmm.
This whole picture of forces in, let's call it a Newtonian worldview,
Yeah.
where everything has a definite location at all times and there's absolute simultaneity uh, doesn't what's simply transfer to the quantum realm. So remember that, as you said, in quantum theory, the theory is, the mathematical form is, in general, something that merely predicts probabilities.
Yeah.
So a force is the analog of a force, to the extent there is one. It's some mathematical operation that changes the numbers in the let's say, representation of a state of a quantum system. A force on the system would just be some operator that changed various, let's say, numbers associated with position probability estimates, position measurement probability estimates. So roughly, a force in quantum theory, to the extent there would be an analog of force, it's a very different kind of thing. It's not a little arrow with a definite direction in space. Let's say it's some mathematical operation that does something to the so-called state of the quantum system. Thereby, let's say, changing the state, but even to say changing the state has this causal implication. Mm-hmm. And if when you think of quantum theory purely instrumentalistically, you might think, well, if this is just a bunch of probabilities anyway, what this talk of cause may not really even apply. All we can ever measure is when certain things happen, they're correlated with certain other things, other points of reading, probabilities of points of reading. And all this talk of causation may just be irrelevant or not fit in very naturally. Whereas force, as introduced in a Newtonian scheme, I mean, one could also be instrumentalist about force even in the Newtonian scheme, but many take it to have some kind of causal connotation. Like a force is what causes a change of state of a certain sort. You know, it causes the acceleration, for example, you might think. Force is actually a very interesting notion in itself. Even leaving aside quantum phenomena, even if you're in a Newtonian picture, it's a very weird kind of entity, right? It's a great example of a theoretical posit. Like, you can't, in some sense, see the force. All you can see is the effects of the force.
Yeah.
So it's like this invisible ghost that we just posit because we say, why did that thing accelerate? Well, let's say there's a force, and then that somehow satisfies it. There's this invisible thing posited in order to help us sleep at night and not think, well, that thing just moved, that thing just accelerated. We say, no, it didn't just accelerate. There was this invisible pusher. And now we're okay. An invisible pusher. Okay, that's great. Now we've explained it. Now we've explained it causally. I'm sort of, poking fun just to give you the idea about how strange when you start thinking about some of these fundamental posits that we take for granted.
Yeah. When
we start thinking about what the heck is a force and why should we think there really are forces metaphysically out there? And aside from just the common sense, well, if we posit it, we can make predictions about how things are going to move, like satellites.
All right. Well, that is very good to know. Everything is just predictions based on assumptions. Well, according to science. Now, I wanted to get to something else that I had found out while in doing some research about people wanting to just say that basically everything could be a form of science, even if you can't observe it, like the supernatural. Do you have any thoughts on that?
Yeah, so I don't have any particularly helpful thoughts in a way, but I could be underselling my thoughts. So here's one thing. I don't think we know what we're talking about when we say supernatural.
Okay.
Like when you press, like what could supernatural come to? So here's an example.
Mm-hmm.
We think of angels as supernatural,
Yeah.
and then you ask, well, could there be angels, I don't know, moving your furniture around occasionally or helping you get out of the way of cars, guardian angels or something? Is that scientific?
Mm-hmm.
Well, if we found there was some systematicity that, I don't know, people that prayed a lot seemed to jump out of front of cars better than others, or, we found some interesting pattern. It's hard to imagine, but suppose we did. Why should we think that's a supernatural phenomenon as opposed to, there are these weird, invisible, not visually detectable, kind of like forces.
Mm-hmm.
Angels are kind of like forces. They're these explainers of various changes of trajectory of human beings. Sometimes human beings are about to walk in front of buses, and then there are these physical manifestations of a force that come and push them out of the way. I mean, what makes it supernatural is roughly what I'm trying to get at with this example.
Okay, so it's basically supernatural until we can explain it in the natural world.
Or you could you could say either something does have some manifestation in the natural world of some sort, let's call it broadly and observable sort. And I want to include the natural world very broadly. So even if, like, you have experiences and you tell me, you know what, the angel Michael visits me and tells me stuff and I can see his face and his wings in my vision, so on. Mm-hmm. And nobody else can see even when other people are there, but I see. I want to allow, if there is an entity in the universe that's causing you visions, again, I ask, and that affects your behavior, you're happier or you're less upset or you feel more confident after these visions, so it has some sort of effect. By virtue of what would such a vision be supernatural? And I don't want to claim there's no way of drawing the natural supernatural distinction. I just want to give you a sense of why it's not as straightforward as we often just take it to be when we just talk about, the supernatural, blah, blah, blah. Like, I don't think we normally have anything definite in mind when we say supernatural. It's some vague sense of a list of things like angels and ghosts or something.
Yeah. I've always wondered that if ghosts are supernatural, yet they exist in our world, wouldn't that make them
what
natural?
makes them supernatural? Yeah.
Yeah.
What would make that a supernatural phenomenon? So that connects to this, could supernatural stuff be part of science? It's somewhat tricky, partly because of what we've been talking about, because you could feel like if something were subsumed into science, it would you could even almost say by definition, it would no longer be understood as supernatural. Mm-hmm. It's almost as though the supernatural is by definition, I'm not saying this is correct, but that's a view one might have, is by definition the sort of thing you can't subsume under any scientific pattern of any sort. But then it seems like the answer is just straightforwardly, no, supernatural phenomena can't be part of science.
Yeah. Well,
but then that seems unfair to somebody who says, well, what do you mean? You're just ruling out angels prior to any observation? Angels couldn't exist or ghosts couldn't exist? But then you have to remember, you have to be careful about what we mean by supernatural. I'm not saying angels don't exist. What I'm saying is, if there are angels and they have patterned effects of any sort, it's no longer clear we should label them supernatural.
Yeah.
And similarly for God, for that matter, for some divine entity with superpowers, if there is such an entity, what makes such an entity supernatural as opposed to an interesting posit of a certain kind of scientific project? The whole supernatural versus natural distinction seems to me more problematic than usually is taken.
Yeah. So I guess the way of understanding it is like a supernatural thing. Like, for instance, if ghosts do exist, or gods, or angels, we only see that as supernatural because we don't really have a way to explain it in the natural world. But when you start to apply science to it, and you can observe these entities, they become a part of the natural world because they interact with the natural world.
Yeah. Or whether, I wouldn't say they become, I would say we then would come to think. Yeah, we would then take them to have turned out to have been natural phenomena.
Yeah. So I guess the supernatural is just our misunderstanding of the natural world.
Or, maybe, unless somebody says more, has some particular well-defined notion of supernatural, then we can maybe engage. But usually I've never seen that, practically never seen that done, where you say, oh, here's what I mean by supernatural.
Yeah. So we are pretty much coming up to an hour.
Okay.
Yeah, I don't want to take up too much of your time. If you have other places to be, I understand.
No, I don't. If we can talk a bit longer, if you want to.
All right.
We've covered almost everything there is to know. So.
All right. Well, that's.
I'm joking, of course. Yeah.
Yeah. Yeah. Obviously. So I wanted to jump into something that happened sort of recently, where scientists were able to detect gravitational waves from, what was it, two colliding stars?
Yeah.
Yeah. And that kind of, I wanted to tie that in with relativity and gravity. And from my understanding, the gravitational waves that they were able to measure were faster than what they thought they would be, if I'm correct.
Huh. Yeah, I'm not familiar with that, actually, that claim. I haven't followed that much. Partly, the history of trying to detect gravitational waves had been fraught with obscurity about what would even count as detection of a gravitational wave and why. Mm-hmm. So I continue to reserve judgment, 10, 20 years from now, if they're still thinking that they've detected gravitational waves, I'll be I'll take it more seriously or something. Mm-hmm. But yeah, it could be that a lot of really smart physicists are convinced this really was the detection of gravitational waves. And then if they travel faster or slower than the theory predicts, then they have to, it's the usual thing in physics, right? You have to say, well, did we make some kind of measurement error? Yeah. Or was there some sort of false assumption that we used? Or should we revise the theory?
Yeah.
And that's back to this fundamental issue that we were talking about earlier. That's a complicated decision that there's no recipe for. Just other than keep making measurements and keep trying to refine and refine and refine.
Yeah. I guess that's basically just how science is. You have a hypothesis that you think is correct, find out that it's wrong, and then you get a different prediction based on your assumptions.
Well, can I say something about that, actually? Popper, who I mentioned earlier, who's famous for trying to give it a way of demarcating genuine science from non-science, his demarcation criterion that still is sometimes given by scientists when they're asked about what science is, they give this falsifiability criterion, which comes from Popper. So Popper thought, here's the difference between scientific theories and other kinds of theories. Scientific theories are falsifiable by some data. They're the sorts of things that we can at least, in principle, construct some experimental situation or observation situation That's such that if the theory were false, we would find out. So I raise that because just as checking theories occurs against the background, this is related to why most, or basically no philosophers of science that I know of now are Popperians. This whole falsification criterion doesn't really pan out. And it's because of this phenomenon. Look, has general relativity been falsified? You just said they made a measurement that didn't fit with the current theory.
Yeah.
So should we just reject general relativity? Basically, short story is that seems very premature.
Yeah.
But why? Well, because of all these possible misconceptions we have about either the devices and how they're working or theoretical background assumptions or what have you.
Yeah.
So there's no such thing as straightforward verification and straightforward falsification either. And that's why it's not that helpful, as it turns out, to say, well, scientific claims are just sort of definitively falsifiable. Well, the problem is pretty much nothing is definitively falsifiable. So either there's no such thing as science if you're a falsifiable, or very minimal, a few things maybe are close to just absolutely definitively falsifiable. But something like gravitational waves is such a complicated experiment with so many embedded complicated assumptions. It's very tricky to even judge, like, what exactly should we do with this data?
Yeah. Yeah, and if it is something that was wrong with one of their instruments, it's going to be a long time before they can measure that again.
That's right. You know, there's this, I learned about a really weird phenomenon. You know, if you heard of the Pioneer satellites?
No.
This was I forget when they sent these out, but they sent these satellites that eventually were going to just leave the solar system.
Uh-huh.
And they put some stuff on for the aliens, if an alien ever found it.
So kind of like the Voyager, if I'm correct?
Kind of like what?
The Voyager, I believe that's what it is.
I forget whether Voyager is doing that, and I may be misremembering whether it's the Voyager or the Pioneer. In any case, it's some satellite that's moving out of the solar system.
That is like a
But it seems to be moving, I think it's moving faster than it should be, according to all assumptions that anyone, and there's been people trying really hard to figure out why this thing's moving differently from any prediction of physics, but nobody has come up with a convincing account. Mm-hmm. And it's like, what do you do with that? You say, well, our theory of gravity is false. It seems like, well, no, there are all these complicated things that could be causing it that we may not have thought of it yet.
Yeah.
And that's the situation we're often in. Scientists are often in. There's just some things we don't understand, and we don't know what to make of the data.
Yeah.
Yeah.
Wow, this has honestly been, I've learned quite a lot from this conversation. You talked about a lot, but thanks for joining me, Professor.
Well, thank you. Thanks for having me on, and good luck on your future podcasts.
Do you have any books or anything out in case somebody wants to, I guess, read more on your work? I only have one co-authored book on a kind of obscure topic to non-philosophers. Mm-hmm. It's on the so-called analytic synthetic distinction. So it's about roughly what the status of definitions is. Mm-hmm. Like, people often say things like, well, define your terms, and, well, what's your definition of consciousness, or what's your definition of mass? And people have a sense that somehow definitions can't be falsified. Definitions you just sort of get for free. They just tell you what the meaning of the words are. And then we go on and do experiments to test other stuff, but not definitions. Yeah.
So there was a controversy. A guy named Quine raised problems with this whole idea of definitions that's somehow special.
Mm-hmm.
So my book's about that distinction. So it's sort of it's the kind of thing that a non-philosopher would find very obscure. But I have also written on, there's something we didn't touch on today, which is the so-called fine-tuning argument.
Mm-hmm.
There's an argument that the constants in the laws of physics seem to be just about perfectly tuned to within unimaginably narrow range, just so that, let's just to put one version, is possible in the universe.
Mm-hmm.
And the idea is if you change a certain constant of gravity, for example, by 1×10⁻²00, let's say, galaxies and stars wouldn't form the way they do, and you just have a uniform hydrogen gas spread throughout the universe, so you wouldn't have any life as we know it. There are various arguments like that. Similarly, for the various constants associated with electric charges or the strong force and other things. So many people have tried to argue for either that there's a God, because how do you explain why these constants are so finely tuned,
Mm-hmm.
just right for the rise so that human life can arise? Theists say that's great evidence that there's a God who created these laws, these constants, set them to those values.
Mm-hmm.
Some others who are not theists say, well, this is good evidence that there are a whole bunch of our universe that we can see as just one of some huge number of other universes, all which have different values for the constants.
Yeah.
So basically that whole morass of issues is the fine-tuning, like how to explain fine-tuning or the fine-tuning problem.
Yeah. Well,
And
I guess I would attribute.
and
that
I've
to,
written on that, yeah.
I would attribute that to our lack of knowledge of the universe. I mean, there's so much that we just don't know.
Well, I think I'm in broad sympathy, but then to say exactly what's wrong with their argument is not straightforward. Took me, I don't know, thinking off and on for several years at least, and I now have my sort of a new response to it. Mm-hmm. But it's an interesting issue. It sort of got a bunch of strands in different areas of science, including the interpretation of probability. So I found it an interesting issue.
Okay. Would you be open to a later interview about the philosophy of language?
Sure, definitely.
All right. Well, thank you for joining us. This has been the Night Talk podcast. Signing off.